All right, so we're back again. It's been a while. We're back with Stan Gibelisco's Teaching Yourself Electricity and Electronics. This is chapter 25, where we left off talking about transistors. Now, one of the reasons, amongst others, has for my delay on this is that I've been really trying to figure out the best way to teach transistors in a practical sense, for just people that want to build stuff. And it's a really large topic. So this is going to have to really be broken down into many different videos, many different segments. Even in this book, the chapter 22 is actually relatively short for the amount of information that there is to cover on transistors, which is all right. I still appreciate the book. Maybe it's one of my least favorite layouts is a transistor chapter, but just having gone through it a bit to prepare for this video, it does cover some good information. There's just a lot of brevity here, but like I said, part of the reason for that is just that there's a lot to cover with transistors. But again, we're going to try to break this down here to teach you guys how to use it in a practical sense, right? We're going to do a little bit of theory and a little bit of the science stuff behind it, but more importantly, what I want you to take away from this video in particular is just how the thing operates. How could I use it? Okay, so we're going to start off, and he starts off here. So the breakdown of this video is I'm going to do a really quick run through of chapter 22 on transistors with Stan Gibelisco. I'm not going to read anything. You guys can, obviously it's always encouraged that you all, read the chapter yourselves, look up some information. You can ask me about some more information if you'd like, or aid in helping me to present another video, giving me some subject matter to cover on transistors for the next video. But I'm just going to skim through this really quickly, and then we're going to go onto the whiteboard, and I'm going to go over just the basic functionalities of a transistor, how to think about them, how do we use them, kind of thing. Okay. So the first thing he does here, which is probably pretty typical, any book, and I think what we're going to do also, I didn't mention this, I thought a good way to also kind of remedy the fact that this is such a large topic and that the chapter in this book isn't as extensive, is that we'll go into the Practical Electronics for Inventors book, and we'll look in that book, and we will use that chapter as well to cover some of this stuff. So a pretty practical setup here, or a very typical setup here, he starts talking about NPN transistors, PNP transistors. If we haven't heard that verbiage before, don't know what that is, so it's N-type and P-type doping that was covered in the diodes chapter, if you all recall, or if you've ever encountered that through your studies. Basically, transistors and diodes are doped. Basically doped meaning that they're basically just given a certain charge, right? The silicon is given a certain charge and it keeps that charge. So an NPN is doped negative, positive, negative, versus a PNP, which is doped positive, negative, positive. Okay. Why is that important to us? Well, there's a couple reasons, and he kind of illustrates some of that. He talks about this at the end here, this last chapter, or this last paragraph here. He starts talking about the interchangeability of the NPN and the PNP, and he's partially right. Okay, so is there a difference between an NPN transistor and a PNP beyond their polarity? Yes, that's the thing. So it becomes a kind of common for people to say, oh, they're the same, you can just switch them. They really just have to do with polarity, which is what he mentions here. But it's not completely true. P-type NPN or PNP transistors have more holes. I want to say that it's more holes that they have, and that actually affects the performance of them. So that is one reason why NPN transistors are used more frequently. Another reason why is just because of the way current flow, our common current flow is set up. So typically, and we've covered this, everyone probably knows this very thoroughly, that typically our circuits are set up with positive on the top, right? Positive voltage is what we feed things, right? And then negative is usually how we ground things, right? So we have it set up so we have positive on top, negative on bottom. The NPN transistor follows that schema, right? Whereas a PNP transistor, and you'll see this, he has this illustrated in other places in the next couple pages here. A PNP transistor, as he denotes here on the at this last chapter, is that we can just change them. We can take a PNP transistor and just flip the polarity of your power supply of your circuit, and then you can put a PNP transistor in there. Would you necessarily want to do that? Well, probably not. Just because there might not be any cause for it. So the idea to take away from this is that if we were using negative supplies, then we put a PNP transistor in there, and we can use a PNP transistor just like we would an NPN transistor for the most part. What's more important here, and this is something he doesn't cover, is more of what PNP transistors, NPN and PNP transistors, are used for most commonly, because there is a place. PNP transistors are very useful. NPN are more common. PNP are very useful. Why? So PNP transistors you'll encounter mostly in current sourcing situations, which have to do with power supplies and with power amplification. Okay, those are the two ways in which you'll see NPN transistors used the most. Everything else will just be PNP. And part of the reason for that, if you're starting to get a feel for and a sense for this, is that there might be some points in a circuit where a PNP transistor could help an NPN transistor accumulate current or whatnot, right? And there might be a certain place in the schematic or in that circuit where it needs that function, but you need something to operate on the opposite polarity, right? So the PNP transistor is good for that. There's also a difference in how we bias the PNP versus the NPN, and we can talk about that later. That's another reason why the NPN is going to be used more commonly. Just to be brief about it, so an NPN transistor turns on from 0 to 0.7, whereas a PNP transistor will turn on from a higher voltage and then needs to have a difference of 0.7. Okay, so they just basically work in reverse, right? It's more common that our circuits are set up to where we want to go from 0 to 0.7 or to whatever our bias voltage is, rather than going from a higher bias voltage down to a lower bias voltage to turn on the PNP transistor. Okay, so we have that covered. Now, let's talk about some symbology really quick, because I don't want to assume that everyone just knows this. So our PNP or NPN transistor looks like this. How can we tell that it's an NPN? It's because of that circle, because of that arrow there that I just drew a circle around. This is going to be the collector, this is going to be the base, this is going to be the emitter. We'll talk about those in more detail a little bit later when we get to the whiteboard. This is going to be your NPN. Your PNP is going to be like this. You can see on the emitter, the PNP junction, or the PNP transistor, the arrow is pointing inward towards the emitter. Okay, and that's how we'll know on a schematic what the difference is. As you can see, here's denoting a PNP or an NPN transistor, and you see the arrow there. Now, one thing to mention is that oftentimes, because of what he mentioned about the polarity, when we don't want to change the polarity of a PNP transistor, we don't want to change the polarity of our circuit to accommodate a PNP transistor. Oftentimes, what designers will do is just put the transistor upside down instead of putting the polarity upside down. So you basically, you're able to keep your circuit like this, and you just flip your transistor. Okay, so you'll see them very commonly, just upside down like that. So let's scroll through some of the next pages here. He talks about biasing, a very important topic, one we covered before because we talked about diodes. Okay, now, again, I'm just going to be brief about this. Remember, a transistor is basically two diodes that are put together opposing each other, just like we see here. This is how he has it illustrated. To get the diode to forward bias, like we've talked about before, the diode lets energy go one way and not the other. To let it forward bias, we need a voltage of 0.7 for current then to flow in that direction. Okay, that's our basis of biasing. Again, we typically think of biasing as in the NPN case of biasing. Okay, and again, we'll cover this a little bit more as we get deeper into transistors. Then we have reverse biasing. That's something that we've talked about before, because I talked about it with respect to diodes. All these things are the same with respect to transistors. Remember, a transistor is basically just a more complicated diode, right? It's just a diode with 3 legs instead of 2, right? So it just has more ways of controlling it, but it has the same function. It has more functions, but it has the same, basic function. So reverse biasing is basically when we hit our breakdown voltage. Remember that we can, depending on how a transistor is designed, we can actually get that current to flow the other way. Most of the time we don't want that to happen. Typically, reverse bias, or the possibility of a reverse bias, is something that's a consequence of how something is set up in a circuit. It's not necessarily something that we desire. Okay. Forward biasing, we just talked about that. That's what typically we're going to talk about the most. We see a curve where we see our forward biasing, then to saturation. We'll talk a little bit about what those terms mean a little bit later. All right, so here we start talking about PNP transistor biasing. Okay, and as you can see here, what he has is the same kind of internal model of a transistor. It's just that he has them facing each other now, with the cathode ends facing each other, and you see that he has the supply voltage flipped over, as I talked about earlier. Now here is the transistor model, and it just has the emitter arrow going inward, and it has the supply voltage flipped. Remember, like I said earlier, oftentimes, and because we're working with a PNP circuit primarily that might have NPN transistors in it, we'll keep the supply voltage, flipped, what I would call upright, conventionally upright, with the positive end on top, and they'll just flip the PNP transistor and operate it that way. Then he goes into amplification, biasing for amplification, which is what we're going to talk about next. And then we're going to talk about common emitter circuits. So the common emitter amplifier, we'll talk about that in our next video. And then, of course, we'll review some of these quiz questions as well. So again, I just wanted to kind of skim over this chapter to see the topics that we're going to cover. And of course, if you're interested in this, go on and do your own research and, indulge in the topics. Just remember that, again, with these videos, this is for practical electronics. We're just learning how to build things, so we're not going to get too theoretical. If you want to get theoretical, the other thing to keep in mind is that the further you go, the further you take yourselves away from practical electronics, right? If we go into something like transistors more and more and more, which can be interesting and it's going to be insightful, but the more we get into transistors, the more you're going to start budding semiconductor engineering rather than doing practical electronics. But the deeper you go, usually the deeper you understand, and then you'll have more of an intuition about how to use these things. This is, again, what we want to build. You want to build an intuition so that when you see a schematic, you know how it operates. So we're going to flip over to the whiteboard, and we're going to see how these things actually function and how to think about these things on a practical sense. All right, so here we are at the whiteboard, and we'll go into some more details about the transistor. So first off, let's talk about the modes of the transistor, and then we'll talk about the common uses. So there are four common modes of the transistor. It's going to be forward active, or as we refer to oftentimes as forward bias. There's going to be saturation, which is basically the point to which the transistor can't do any more. That's usually talked about in terms of amplification. Okay, so basically it's hit its wall as far as amplification. Then we have reverse active or reverse bias, and then we have cutoff, which is that it's not operating at all. So common uses of the transistor. What are transistors used for the most? Well, we have switching. Okay, and that can take place typically nowadays. Switching, as far as transistors are concerned, is going to take place in power supplies. Then we have amplification. That just takes place everywhere. I would also put in amplification, I would put buffering as well. That would be something there to put. Because, sometimes we don't always think of necessarily amplification as not always making a signal larger, even though that's what it means. Amplification can also buffer signals, which is in a lot of cases essential, especially because of an impedance transfer. Then we have current sourcing, which is what I talked about with respect to the PNP type transistors. Okay, so those are the three most common functions of the transistor. Now let's figure out how this thing works and how we're going to use it, more importantly. So remember earlier when I was drawing this out, I made a comment about these different nodes. And of course, again, we're going to be working with an NPN transistor, okay? Pretty much all the time, where you can just assume, of course, if you see the arrow, then you know, but pretty much all the time we're going to be working with an NPN transistor. Now this NPN transistor is going to have a collector, an emitter, and a base. Now, lots of times, people like to look at this as a three-way valve, you can say. Okay, now the point about this is that this transistor basically has these three different nodes that are typically going to be used in this fashion. We'll have the collector. It's typically going to be our output. The base is going to be our input. And the emitter's going to go to ground. It's basically like a ground reference. I mean, there's all kind of things that happen with the emitter respect to the base and with the emitter respect to the collector. You have to remember this is all relational. So when you see, like when we look at, which I've done on this channel before years ago, we have to probably revisit that, is looking at a data sheet. If you look at a data sheet, it'll show you some characteristics of the base junction with respect to the emitter junction, or the base junction with respect to the collector junction, and the collector junction with respect to the emitter junction. So these three junctions are all working respective of each other. And that's something that we'll start to gain an intuition and understanding of as we start to work with them. But just know that this is the setup. This is the way we want to think about them most of the time. Remember, again, you can use a transistor in many different ways. You can use a transistor to where we have the collector, and this is when this is happening, we usually write it like this. When this is happening, we can use the collector as the input, and the emitter as the output sometimes, depending on our desired outcome. So this is actually a typical way that even an NPN transistor will be used in like a power supply for current amplification. I don't want to get too much into different situations. I just want you guys to understand that even though this way is number one, right? This is the primary way in which we're going to look at it and use it. It can be used in other fashions. The reason why it's used in this fashion most of the time is partly because that's how it was made to be used, meaning that this is where you experience the most benefit when it comes to most of these functions, okay? Switching, you can virtually do switching any kind of way. Amplification factor is the important one. When we're looking for amplification factor from our transistor, we're going to get the most amplification using it this way, all right? That could also be true with current sourcing as well, depending on what's going on. So this is the primary way we're going to set our transistor up. Now we got to figure out how to turn the thing on. So we're going to take the thing and we're going to put it basically in a schematic, right? What I have here is I'm just labeling what we call the pinout, right? This is just a pinout of the transistor. It shows that we have a collector, base emitter. This is used, and I'm using, you can look at this as a common emitter, right? This is kind of a common emitter function, which like I said, is very common. But they say common emitter because common is another way for ground, another word for ground. So when the emitter is common, this is what we have. Or sometimes it can be called a collector output, right? Because the output's at the collector, the emitter is grounded. So we're going to use that kind of same scheme to give ourselves an understanding of how we would actually use this. And this is one place I really like to start off. And it's with the LED example. I feel like this is one of the most intuitive and kind of easy to understand ways to understand the operation of a transistor. Again, NPN transistor in common emitter mode, which is the most common setup that we see for transistors. So what's happening here is I have a battery. I'll even put this, let's put this in a different color here. So let's put this in red as well. So this is the positive terminal of the battery. This is our ground. Our ground is connected to the collector, or the emitter. And we have an LED, or a light emitting diode. Okay, we have an LED there, but I'm actually gonna, just so remember, that's the symbol for an LED. For this moment, I'll leave that off because right now the LED is not on. The question here is, if there's a battery connected, let's say this is for the sake of being slightly more accurate, we'll put a resistor here. We'll put a resistor here. And that's our circuit components in the red there. So if we have a resistor, I don't know, let's say it's a 100 ohm resistor. If we have a 100 ohm resistor, and let's say this is a, let's say it's 5 volts. Okay, we have 5 volts here. if this LED is connected to this 5-volt power supply through this resistor, and the resistor is there for current limiting. Remember, LEDs will basically detect and live by current. So if you just hook it up to a current source, some kind of power source, it's going to want to take as much power as is available, or even more, until it blows out, right? This is why we need the current limiting transistor, or the current limiting resistor. So if this thing is hooked up to a power source, it has a current limiting transistor or resistor, why isn't it on? Remember, the LED is not going to come on until I put the stripes there that shows that it's emitting any kind of light. The LED doesn't come on basically because the cathode end of the LED, which is denoted by that red line, is connected to the collector of our transistor. So then, to figure out what the LED is doing, we have to figure out the condition of the transistor. The condition of the transistor, well, if this LED, or if this LED, the power is going through the resistor and the LED through the collector, that means that the transistor has positive voltage, right? It does, and on one end it's grounded. But why is it that if this transistor has positive voltage on one end that's going through this resistor, through this LED, at the collector, and its emitter is grounded, why doesn't it see any voltage, or not enough voltage to turn this on? Well, the answer is that there is voltage present at the collector, or nearabouts, but there's not a completed circuit, because this end of the circuit, essentially, this end, does not see what's going on at this end, because the transistor isn't conducting. Okay, this is what we would say the transistor is basically, it's at cutoff, right? It's not operating. It's, again, like we talked about, basically like a switch. It's just a voltage controlled switch, and we need that 0.7 volts, typically at the base, to turn the transistor on. So what we don't have here is we don't have any bias voltage, and that's why the transistor isn't conducting. So if we, and I'm just going to do this, I'm not going to, or we can say, we can be theoretical here, because I haven't figured out these values. I'm just, doing this off the cuff here. So let's say we need a certain amount of bias voltage. We need at least 0.7 here. I don't know, let's say we're going to even put 1 volt there. So we'd have to have a resistor here. Let's say we have to have, I don't know, let's say we had to have a 1K resistor. Okay, so if we now implant that 1K resistor to bias this this transistor, is it going to turn on now? Yes. And that's what will allow the current to actually flow from this end to there and have a completed circuit. Now the LED turns on. So that's your basic function of a transistor. Okay, that's your switching function of a transistor. When we don't have any bias current, any bias voltage, like if this wasn't here, if we take that resistor back out and our base isn't biased, then the thing doesn't conduct, and that means that whatever on this side, or the other side for that matter, it doesn't see anything else. It can't complete the circuit. Because remember, just because the LED in this case has a positive voltage, it doesn't have anything connected to itself, right? It doesn't have any reference towards ground, is what I mean basically here, right? This LED doesn't have any reference towards ground, so it can't complete the circuit. As soon as it has reference towards ground, it can then conduct and complete the circuit. What does it need to complete the circuit? Well, we just need a resistor here. That's going to give us that 0.7 volts or greater, right? Greater than or equal to 0.7. That will bias the circuit. That then allows the circuit to be complete, and then the LED shines. So that's a primary way in which we get away from using mechanical switches, right? And you're basically using an electrically controlled switch here. So let's say, for instance, you'd say, well, what's the point of that? You know, well, let's say if we wanted to make this LED flash, right? An LED flashing circuit has been a very popular circuit since electronics came out, right? There's multiple ways of doing it. One way to do it like this is if we had, let's say we had like a 555 timer. And we got that 555 timer to output a certain frequency. Let's say it was, let's just say it was 100 hertz. We have 100 hertz at 0.7 volts that would come out of that 555 timer. That means that you'd have a 100 hertz cycle for that voltage, so it would go on and off 100 times a second essentially, which would be, in this case, which really in a lot of ways that would be way too fast. Let's just actually make it pulse. So let's just say it was just 2 hertz, so it just happens twice a second, right? Because remember, our light bulbs go at 60 seconds or 60 times a second, and we can't detect that with our human eyes. So something faster than that isn't going to work either. So we may have to make it much slower. So if that thing goes on and off, and the 555 timer is just going to give us basically a square wave output where it just goes high. And in this case, our high is going to be 0.7, and then our low is going to be 0. So it's going to go low. When it's low, the transistor is not conducting. When it's high, the transistor is going to be biased, so therefore it's going to conduct, and then the LED would come on. So that's the basic idea around our transistor. Okay. Now you could take this circuit, and you figure out, if you have a breadboard, you can figure out what bias voltage you might need to bias the base, and you put a resistor there to bias the base, and you have a completed circuit that will work. And we'll do this on the breadboard as well. We can do that in a demonstration video. But again, this is a large topic, so we're going to do it in small pieces, small bites. Next time we'll probably go into a little bit of the amplification factors of a transistor. I'll be looking at the data sheets as well, and we'll talk about common emitter amplifiers. It was nice to be back with you guys again. I hope you guys enjoyed it. I'll see you soon.